Hi, good evening. It's been quite a few days since I tried recording a video or something. I was not actually interested in doing that because I had many things. My work was going on. Then I tried gaming and all. I was interested in a brief period in gaming or reading up mostly. And also, I was very much um, drawn to the present social issues. So I didn't want them to come on in the videos I make. And okay, so anyway, this series of videos that I had made or am making are mostly because of my good friends Manish, and he initially suggested me this idea to make a video for him actually because he just started with his PhD and he wanted to he had some doubts actually in some few topics. Initially, it was just in some basic softwares, then in few concepts. So he asked me to teach him in Zoom or Google Meet or something like that. Then I was a bit reluctant because I know once I teach them again, if he has a doubt, he'll again call me and something. So he suggested that I make a video and send it. And also, it was the major reason was that our time zones don't match because I think I live 3.5 hours behind India and now it's 4.5 hours. So he suggested that I just make a video and send him, then it would be good. So initially, these videos are all private. I don't know why I started making them public. Anyway, here we are, and so today we see about XRD, the X-ray diffraction, and the basics of it, or I would say very very basics, because I won't be going into the how the diffraction actually occurs, the law of diffraction, the equations and all. Maybe if another day I may make or may not make, I don't know about those topics, but in general, very basics of X-ray diffraction, which are I think good to know before you start doing XRD or something. So yeah, I'm trying to write on my laptop using these pens and all. I don't know how they come. However, yeah, I think this is always better because you can control the thickness here. No, I want a bit thinner. Yeah, fine. So first XRD. So the thing is that why do we need XRD, or what does XRD show or things? Um, so why do we need XRD? Because we all know, let's say we have a crystal. So we have a crystal and we have these planes of crystal. Let's say any planes interplan. We all know the planes, interplanar spacings, and all those, right? Let's say we take this plane. Then in the next crystal that you have the same plane. So this the distance between these two planes, this is called as d spacing or the interplanar spacing. And the reason we use X-rays and not others is because this spacing between these two, or Yeah, the spacing between these two, this is of the order of the light wavelength of X-rays. And what do we mean by that? We all know that diffraction occurs whenever the light bends around a structure, right? Suppose you have, let's say, an object. Light is coming, the light will only bend when the light is of some order of wavelength around the size of this object, comparable to this object. And we know the Young's double slit experiment, right? So there is the constructive, destructive interference and all such. So like the constructive interference happens only at few points, then there are nodes at which destructive interference happens, then we get a band like pattern and all these things. Of these are very basics of diffraction. And so this uh, interplanar spacing, the order of these interplanar spacings, they are generally in the comparable to the order of X-rays. So that's why we use X-rays, not another light source. So that's the reason we use X-rays. And so what does it show? Or first is the, as you know, structure. I think I'll better type it out. Structure. Then also it shows the stress in the structure. Or you can say stress and strain. Then here I mean by structure it's crystal structure. Stress strain. Then here you can have phases. These are some general things which we can do using an XRD or using X-rays. So then also, yeah, we always see an XRD graph between 2 theta and intensity, right? Something like this, 2 theta and intensity. So this theta or 2 theta, we know how we, or it is at least measured. This intensity we write, or here we write degrees, something like that. You know the units of this 2 theta. I supposed to say this. Yeah, you know the units of 2 theta is in degrees, but intensity we write arbitrary units. And what is this arbitrary units, or what does it depend on generally? So this one depends on the first is the Lorentz factor, then you have the structure factor, then you have the Debye factor, multi multiplicity, and then you have the absorption. Yeah. Sorry, I'm not so good with spellings. So this intensity, this depends on these factors: Lorentz factor, structure factor, Debye factor, multiplicity, and absorption generally. So these things determine the intensity of diffraction. Then we first see how these X-rays are produced. So we may have seen many things called as copper X-rays, cobalt X-rays, molybdenum, iron, many things. This then you can also have gallium, all such sources of X-ray. So what does this mean? To know that, or before we get into it, we first see how X-rays are produced. So first there is a tungsten filament. This is generally what we see in our yellow bulbs, or the bulbs we used to have in olden days. The I don't remember what they were called. The yellow colored bulbs, 100-watt bulbs, which you may find in some random electronic shops nowadays. They were available for 10 rupees each, or I think something. Those have the tungsten filament. That same filament is used, yeah, but maybe a better pure one, not so as cheap as a 10 rupee bulb, but yeah, the principle is the same. So when we heat this, or this is maintained at a negative charge, or we apply a negative charge to this. So due to this, these electrons are emitted from this tungsten filament, and this takes place due to thermionic. My writing is bad. So this electron emission happens due to thermionic emission. Then once these are emitted, you have here what is called a target material. This is at a positive charge. So these things are the target material. These are the target materials. So these electrons, they come and hit the target material. So yeah, and you may have often seen something like the what is it, the voltage or acceleration voltage of the X-rays. So the voltage that is being maintained between these two is called the acceleration voltage of this X-rays. It is generally between 30 kilovolt to 250 kilovolt. Like this is the maximum we have, but generally lab X-rays work at 30 or 50 kilovolt. The more power you give, the more electrons would be emitted, obviously. Then the bet or the higher intensity of X-rays would be coming in. Okay, so now that the electrons we see hit this target of copper, let us see what happens then. So here you have a copper. Let's say these are copper. I'm not seeing the electronic configuration while drawing it, but you get the idea. These are electrons, and this is the nucleus. So once these tungsten electrons, this electron, let's say tungsten, from tungsten, yeah. So these things are coming. One thing what it does is it goes to the inner shell, and due to this going to the inner shell, the electron of the inner shell, it goes out, like it ejects the electron of the inner shell, and here it forms a vacancy. So let's say a vacancy is formed. I'll put it as a box. So first we understand this is step 1, this comes in. Step 2, this goes out. Step 3, in a vacancy is created. Then step 4, this jumps in this vacancy. The electron of this shell goes into the vacancy. This is the step 4. And when this happens, this releases an X-ray. So this transition, this actually releases energy, because when you have atoms or when you have electrons jumping from one level to the level below it, it releases off some energy. Because let's say this is E0, this is at E1, E2, etc. So always, and let's say this is the ground state or the nucleus. So as you go higher up the shell, the energy increases. So when it comes down one level, some energy is released off. This energy is released off in the form of X-rays. So when this happens in, let's say, um, when this happens from, okay, when this happens from, this is K, L, M, and all these shells are named K elements. Okay, you may know this, or if you don't, you should start reading quantum basic Niels Bohr model and quantum mechanics and such things. So okay, this is basically fine. So once this comes L to K, that is from here to here, the electron comes. This is called as K alpha 1, then M to this K, this K alpha 2, some or M to L. I'm not sure this K or L. So this is how K alpha and K alpha 2 radiations come on. So once we saw now one possibility of the electron, that it comes um, it comes into the this one, ejects an electron out of this, and the X-rays are produced. Second thing what can happen is, this same tungsten electron, it can come into it, it goes, it has a high energy, it goes directly to the nucleus, but this nucleus is a positively charged one, and it is copper nucleus, so it has large number of protons, so it's highly positively charged. So this goes off, like this gets deflected due to the, I don't know why I'm not able to draw. Okay, so this gets deflected. This is still the tungsten electron. Okay, so this is still the tungsten electron, it just gets deflected. So we call these things as the X-rays that are released here. These are called as characteristic X-rays, because they are characteristic of the K to L to K or M to K or M to L such transitions. So they are called as characteristic X-rays. Then you have here the rays which are, then you have the rays which are called as Bremsstrahlung X-rays. So Bremsstrahlung X-rays are also released when this happens. Like this is just an electron. This is not the X-ray. So this is not the X-ray. The X-rays associated with this are called as Bremsstrahlung X-rays. And why this comes up is because when this electron goes from like around the nucleus, it loses its energy. So the electron is coming like this. Let's say it has some x keV of energy. It comes near the nucleus, it loses its energy because it's a positively charged, and it is decelerating. So it gets decelerated, and by the time it comes, let's say it goes to y keV, and so um, y is very 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 smaller than x. So this, you understand that when it goes near the nucleus, the electron just decelerates, and due to this deceleration, we have the production of X-rays. Here also these X-rays are produced. These X-rays are called as Bremsstrahlung X-rays. So these the Bremsstrahlung X-rays. These X-rays are the characteristic X-rays. So now that you know two type of X-rays are produced, which one is used in which? These beam strassing X-rays, these are generally used in X-ray fluorescence or CT imaging, computed tomography, and all such things. And these characteristics are generally used for XRDs. So yeah, why do we use this in XRF and this in CT and all? Because this is characteristic X-ray. Why do we call it characteristic? Because this wavelength, what it is there with this X-ray, this wavelength is constant. Okay, so since this wavelength is constant, we call them as characteristic X-rays. Then the Prim Strassling X-rays. Okay, I'll take a new slide. So the Prim Strassling X-rays, these are not characteristic. Like lambda is not constant. Okay, lambda is variable, or it's a spectrum. So you have lambda of lambda is not constant, it's just a spectrum of X-ray or a spectrum of X-rays. So and there is the third or most commonly happening thing which I'll shown now. This, you have here your copper target, as I said. Then your electrons from this tungsten are coming, as I said. One goes to the characteristic X-ray, another goes to the Brem Strassling X-ray. So this is very small parts. Both of this is actually very small in intensity, and it is not so easy to get the Brem Strassling X-rays. Characteristic X-ray is comparatively easier to get, but majority of these electrons, they just heat the substrate, that is they just heat the copper target. So majority of this is lost as heat. The energy that we give as 30 keV or something, this is majority of it is lost as heat. Some of it goes to characteristic X-rays, very less percentage of it goes to Bremsstrassling X-rays. That's why when you see any XRD machine, they have a big chiller, and this chiller is just used to keep this target as cooler as possible. And if this is not cool, then X-rays can't be produced. So now we know how X-rays are produced. I think it is easier to understand now. Although this is fully of mostly looks like a rough one, but now you know how it is produced, right? Then there are XRD modes. So these are the commonly used two modes of X-rays. One is the Bragg-Brentano mode, and another is the grazing angle XRD. This is generally used for powder sample, and generally these samples are bulk. So powder sample in general means a bulk sample, and also thin films with substrate. So suppose you have some silicon substrate, on it you have a thin film of, let's say, any metal or something, or anything, oxide or nitride or something. you use this. This is also called as theta to theta mode. So in this Bragg-Brentano geometry, generally your sample is this. This is the input X-ray. Let's take it as theta. So this is theta and this is also theta. So here you have 2 theta. Then your detector is this. Your X-ray is this. So this is also called as theta to theta mode. Then grazing angle XRD. What happens in grazing angle XRD is this is just used for surface and also thin film without substrate. That is, if you don't have any substrate, it's just a thin film. The thickness of this thin film should be very low for this one, and this also used for depth profiling. And in this one, the X-ray that is coming, this is a constant, and this detector, whatever is there, this moves. The X-ray source is constant and detector moves. So this happens at a fixed theta, or alpha. So this happens at a fixed theta or alpha. Then so here I talked about thin film. So how thin should be this thin film? If you think about in that direction. Okay, so let's say I have a thin film. How thick should be this thin film is it is just 200 micron. If it is less than 200 micron, it is grazing angle XRD, and it is more than 200 micron, it is normal XRD or the Bragg-Brentano. Okay, so this 200 micron is generally a good figure to just remember that if you have a thin film less than this, then you should use the grazing angle XRD or GI XRD, and if it's more than that, you should use a normal Bragg-Brentano geometry. Why is this? Because this grazing angle XRD, this incident, this angle is very low actually. So this is very low angle. So your let's say this is your sample or surface or something. Then your X-rays, they just graze the surface and they just go like this. So they don't go to a very high wavelength, like very high to theta also. They are just in very grazing type of angle. So that's why it's called grazing incident XRD or grazing angle XRD. Then, okay, what we get from XRD? I think we saw it from the first slide when we saw about the introduction or the importance of XRD, but still, I would again mention it. don't know. Just give me a second. I'm trying to figure out some things in this PPT. The only thing is, I don't know how to write in this. Why does PPT have to be so bad? I mean, it's such an easy software. They could have provided a scroll bar here, or am I doing something wrong? I don't understand. Okay, yeah, fine. Hmm. Okay, so what do we get from XRDs? First, we know is crystal structure. So, is it cubic, monoclinic, triclinic, tetragonal, rhombohedral, or if it's cubic, is it FCC, BCC, HCP, or generally the structure? What is the crystal structure of this material? And the phases, or we can also write it as phase information. Then you also have the stress strain. So stress strain in the crystal, these are generally the things that we get in from the XRD. Then also, if it's a single crystal, let's say, for a single crystal, the rule or it's generally the grain size is equal to the crystal size. This should be fairly easy to understand because single crystal just means a single piece of a crystal. It's just one crystallite. So whatever the crystal is there, it's just the grain. So it's just one grain, but polycrystal grain size is not equal to crystal size. This should be fairly easy to understand, I suppose, because the single crystal is defined as such that all the planes are oriented in the same direction, or all the planes are oriented in the same way. It's just one grain. But in a polycrystalline material, this polycrystalline material, it has many crystallites or the grains. So obviously, grain size is not equal to crystal size. Crystal consists of many grains, and so it's bigger. Then okay, parameters, or what does this peak things depend on, or something we already know from. So for intensity, these are the parameters. For intensity, it depends on Lorentz factor, structure factor, debye factor, multiplicity, adsorption, on all these things. So then, what does the shape or things uh, depend on? Peak shape depend on? It depends on the strain. size and the instrument or instrumental corrections, or we can say instrumental parameters which we later correct. So I've just written because it should be instrumental parameters. So the we know now what the XRD intensity or and the peaks depend on. Then we also then should know like, yeah, while doing an XRD practically you encounter these two things called as step size and then time per step. These two things, and also theta min to theta max. These four are the general parameters that you use. Also in some machines, like if you don't want to change the instrument settings, it's fine, but sometimes we want to change the instrument settings. You also have the current and the voltage which is there. This is the accelerating voltage and accelerating current that I was talking about. This also affects your intensity but not the shape or the position of this peak. So it's kind of, let's not get more into it because it's generally depends on the facility that you take an XRD, and it's either you take at a low current voltage or high current voltage. There is not much of a difference rather than the intensity. So even the shape stays the same, it's not relevant. So relevant things are step size, time per step, and 2 theta min and 2 theta max. This you understand 2 theta min and 2 theta max. So how do you decide 2 theta min and 2 theta max? Honestly, I think if you are starting with this question that how do I decide between what angle should I take an XRD, it is high time you start reading some literature of your samples or material or the area at least that you're working in, because you only get this doubt when you have not even read even one, not even read, it's more like you're not even tried to open even one XRD image or a paper. If let's say you have a material and you at least read couple of papers even in it, you would notice that okay, people are doing between some x value and some y value, because see some materials show peaks at a lower angle, some shows in a mid range, and some shows far angles. So it depends on the material. I just don't also not want to just shrug it off my shoulders saying that it depends on the material. No, that earlier when I was in my bachelor's and master's, whenever I asked some questions, many people gave this answer saying it depends on your material or it depends on your state of study or the properties that you're aiming for. I don't think that's a good answer, but yeah, what I mean is by depending on material is, I'll tell you an example. Let's say you want to do a mexine, right? XRD of a mexine or mexine material. Your first peak that you have, I think this occurs around 7 or 8, if I remember correctly. It's less than 10 degrees, between 5 and 10 I think it comes. So similarly if you do morph, this is a mixing. Similarly if you take a morph material, even in morph, this, okay, so this comes around 6 degrees, 6 or 7 degrees. This I think is not 7, it was 11 degrees I think. I don't remember very correctly, I did since many years ago, but still you have less than 10 to 15 degrees. This comes at less than 10 degrees. This is morph. In morphs this is the case. Let's say in oxides, peaks generally start after 20 or something. The sulfur, the first peak you would see is around after 20 or around 20. So in oxides it's okay if you take 20 to 80, because generally by 80 all the peaks are done. In mixins you have to go by 5 to let's say 80 or 90 or whatever. Same in morphs, 5 to 90 or something. So This is what I mean, depending on material. If you take a machine and start the scan with 20, you won't get this peak. And this, as far as I remember, a characteristic peak which shows that machine has formed from the max phase. And if you don't see this peak, it means it has not formed. So you may miss out on some peaks and you have to repeat the experiment. Same with MOFs, there is a characteristic peak and you need it to show it that MOF has formed actually. So just read one paper, you would get an idea of these ranges. If let's say you don't want to do that one also, you are very lazy, the easiest I suggest is 10 to 90. Generally all class of materials are covered, or if you don't want to take any risk, just take 5 to 90. I think this would take a bit longer time, but it is the dumbest possible thing to do, but it works, so your wish. Okay, so we were talking about step size and time per step. This 2 theta is done. No, step size, how does it affect? Let's say you have a peak, right? Something comes like this. So something comes like this, then what is the difference between these three things? This is the step size. Point 1. So if you go even further, this would be even easily or better resolved. Maybe you would get something like a very good peak for 0.01 or something. So the idea is that between two angles, if you give a very slow step size, then you measure each point better, so your resolution of between two peaks would be better. Like you won't have much convoluted peaks. So then you have scan scan time. So how does scan time affect? You might have seen some x-rays which are like this. So or this is time per step. What I'm talking about, some x-rays are like this, like they have very high background or something. Then you might have seen some x-rays like this. Okay, I try to find some examples for this. I'm connected, right? Why does it say it's no, not connected? Stupid Google. Okay, yeah. See this pattern? You see the amount of background in this pattern, right? This is very high background, and let's see some other image which shows good patterns. Hmm. This is also one example of very high background. Not a good XRD. If you want to resolve crystal structures or something, it's highly not recommended to do such XRDs. This is more your waste of time. It's better you get a better XRD because you can't refine this. This is just, what do you say? Let's say you work on some materials where XRD is not at all important. which I think is highly doubtful because in material science the basic thing that you do is XRD. But still, if you have, let's say, less access of instruments, or you just have one pattern, you don't have other option, then only go with such patterns. Else please don't go with such patterns, because you see the peak. Yeah, there is a peak, but there's also quite high background. So maybe let's say I have a peak here or here, I won't know it due to the background. I'm not getting some good XRD patterns. Why is it? Let's just try and make outside XRD. Okay, still fine. So yeah, you already saw this background one. See this XRD. Hmm. This is a very good XRD now. I see this. You know, there is very less background. I know this has been taken in a. Okay, this is not clear, but still, it has been taken in a very less step size of very less step size. So this gave a good pattern because the background is very less, and also your peak resolution is good instead of something like this where, you know, if you zoom into this graph, you have a peak here, 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 here there are a multitude of peaks, then here there are a multitude of peaks. This hidden peak, this peak got hidden, there is a peak here, there's a peak here, or there are chances of peaks being here. So but since that this scan was performed at a high scan rate, you never know. So yeah, so I forgot to write. Yeah, let's, when you, if this was 0.1 second per scan, this would be higher scan rate. So let's see what a very good pattern, or this would also have some little background. I'm just showing for comparison. This would be, let's say, 5 seconds. So 5 seconds per scan. Like, the logic is that the higher time you can go, the better scan with less background and better resolved peaks, and the lower step size you go, the better resolved peaks. So that's how these parameters are decided. You have step size, time per step, and 2 theta min max. Okay, now another question comes: what should I use for step size or time per step? This also honestly should be decided by you, because I had people who called me in middle of an XRD slot asking what should I put when they first did XRD, saying what should I put as step size. I always suggested, if you're going for any technique, let's say even it's XRD, Raman, same time, XPS, anything, just read a paper, or not even a paper, just go through basics of the technique. If you don't have time for any of this, just read the Wikipedia page of that specific technique. If you want to go for an XRD, just read the Wikipedia page of XRD, it's more than enough. Just don't go blindly with samples in a packet, because you are doing a research, or you're a research student, and it's not expected of us to go like that. But still, so what step size or something should I use? 0.02 degree per minute. 0.02 degree would be a good step size. Then let's say if you want to use time per step, I don't exactly know the time per step, but 10 to 90 with the 0.02 degrees step size. If you have, for this measurement I am saying, so you can calculate based on that. For this measurement, if you have, let's say, 1 hour slot, the ideal thing to do would be just 1 hour of one sample. But practically, since these slots are on a payment basis generally, and XRD, these facilities are also on a payment or booking or something like that, you have time limitation. It's a good idea to go for 4 samples per hour, or if you have like many samples, go for 6 samples per hour. Don't go beyond 6 samples per hour, because 4 samples per hour, which means 15 minutes, 6 samples per hour, which means 10 minutes. I don't know the seconds per step. You can calculate if you put in anything like, you take a calculator, 10 to 90, it's 0.02 degrees. I have 15 minutes of time. What is the step, like the time per step? It will tell you. If you don't want to do a calculator, you can just go to ChatGPT and put these things. It will tell you. So similarly, 4 samples per hour or 6 samples. This is better. So I think this is for 15 minutes scan. It's 0.25 degree per second. If I am not wrong, or if I remember correctly. If I don't remember, I don't know. But this is generally this thing. I think that is there. 0.25 degrees per second. So, oh sorry, 0.25 not degrees. This seconds per step. 0.25 seconds per step. So this you can use for, ready reference if you don't want to do any kind of hard work or anything to read about. So 10 to 90 or 5 to 90.02 degrees per step and 15 minutes per sample is should be good enough. Also depending on instrument, but yeah, just should be workable. So also if you go lower and lower, let's say you start with point 0.1, you go to 0.0 to 0.01, you go lower and lower in this step size, the background also increases. So just keep that in mind. So and what else is left? I think, yeah, one thing I forgot to mention here. So the x-rays that come out of this, or these characteristic x-rays, whatever they are there, here we have the characteristic x-rays. So these x-rays that come, these are generally the lambda is fixed, but even though the lambda is fixed, there is a very small deviation in the, what do you say, there's a spread in the lambda. It's not, if it was ideal case, then your lambda would be just a straight line, but it's not an ideal case generally. So the lambda is a very small difference, and this difference is reduced by using a monochromator. This is also called as a filter for this. And these diffractions, if you have noticed, or if you studied these diffractions, crystals are one of the best diffractors for X-rays. So the obvious approach here is to use a crystal. We use a crystal here, and this crystal, it filters out the X-ray. So this lambda is more or less constant. This also varies by very tiny bit, which we can correct during retweld. But generally this works as perfectly as possible, and the crystal that we use is germanium. Germanium crystals are used as a monochromatous. So yeah, I think that was the things with the basics of XRD. Have a good day.